Hello, my name is Wesley Lewis. I'm a third-year computer science student at the University of Virginia. During my time at the Robotics Institute Summer Scholars Program, I worked at the Robotics Caregiving and Human Interaction Lab under the mentorship of Dr. Zachary Eggerson, Kavya Putavito, and Akil Padmanabhan. Throughout this program, I investigated using spectroscopy to identify substrates within containers. The title of my research is Container Invariant Classification of Substrates Using Spectroscopy. So what is spectroscopy? Spectroscopy is a study of the absorption and emission of light and other electromagnetic radiation by matter. Common fields that use spectroscopy are chemistry, material science, and even physics. Spectroscopy allows the investigation of the composition and structure of matter at an atomic level. The tools used in spectroscopy are called a spectrometer. It is a measuring device that collects light waves. Those light waves are used to create a frequency spectrum and can be used to determine material. The most basic design of a modern spectrometer can be seen below, where you have a light source, which passes light through a slit onto a diffraction grating, where a mirror can be used to focus onto a photodetector. The light that reflects onto the detector is picked up by individual wavelengths. A subfield of spectroscopy, and a type that we will be using for our experiments, is called near-infrared spectroscopy. It has a wavelength range of 780 nanometers to 2500 nanometers. It is a technique that uses near-infrared electromagnetic radiation to analyze spectral and compositional characteristics of a sample. It has been applied commercially for agriculture, farming schools, and more. So, why near-infrared spectroscopy? Near-infrared spectroscopy has many pros, such as not needing sample preparation, and there have been many recent developments for handheld near-infrared spectrometers, which allows easy attachment to a robot gripper. Previous works have also proven that near-infrared spectroscopy can be used for material classification. Some questions we want to answer throughout this paper are: can near-infrared spectroscopy be used to classify materials that are obscured or visually similar to other materials? Can we estimate substrates across containers? Or can we generalize substrates in a container we haven't seen before? This can prevent many visual issues robots face when given identical objects or are in a crowded situation, such as a fridge, or the situation where a robot is given 2 glasses with cow's milk and almond milk. In our experiments, we will take 10 samples of 36 substrates using 16 containers, making a total of 5,760 samples. The data will be collected using the Mentorship Spectropod, which is a handheld infrared spectrometer with a wavelength range of 850 nanometers to 700 nanometers. We will then train our data using random forest support vector machine and multi-layered perceptron. The method in which we collect the data is pretty simple. First, we will collect the data through the spectrometer. On this slide, we show 2 containers. One, a high-density polyethylene, and the other, a blue glass. On one side, it shows full of ibuprofen. On the other side, it is empty. This graph shows the signal differences. Then, we will standardize our data. The formula for that is shown below. After standardization, we will input the data into models: NMLP, SEM, and random forest, and we will validate each model once using certified k-fold, and a second time using leave one group out. The table here shows that SVM has the best results for certified k-fold, and random forest has the best for leave one group out. It tells us that with the SVM, it is possible to estimate substrates across containers we have seen before, but our overall performance of leave one group out tells us that it is hard to generalize across containers. For future steps, we plan real-world documentation, which will include a robot demo and introducing a second spectrometer to increase the electromagnetic sensor range. We also plan to improve the signal-to-noise ratio. I would like to thank my mentors at CMU and my collaborators Nathaniel Hansen and Donnell Furlang at Northeastern for their guidance and support. I would also like to thank Rachel Burson and Dr. John M. Dolan for coordinating risks. Thank you.